My name is Jacob Crabtree.
My name is Elizabeth Frericks.
And my name is Natalie Willett.
Our senior design project is focused on how an actively controlled detention system helps to mitigate flooding. Our advisors for this are Dr. John McMain, Dr. Alicia Modenbach, and Dr. Michael Peterson.
Worldwide, over 200 flood events accounting for $100 billion in damages occur annually. During 100-year or greater rain events, traditional basins are incapable of reducing peak flow. This inability to manage peak flow can be reduced with the integration of an active control system into existing basins. A scale model will be constructed for a two-basin system draining to a watershed to show flooding scenarios for the education of civil engineers and city planners.
Throughout the last 20 years, cities have been experiencing more frequent and severe flooding. A big part of this change is climate change, which leads to storms becoming more intense with the same amount of rain falling in shorter periods of time. In tandem, new urban areas are being developed and existing urban areas are growing larger. Within these developed areas, land is paved over for roads, parking lots, and buildings, increasing runoff since less water can sink into the ground. Because of these trends, the number of individuals in flood vulnerable areas has grown dramatically. To address these increased vulnerabilities, civil engineers are looking for solutions and improvements to existing stormwater systems. One promising way to address growing flood risks is through actively controlled detention basins. Unlike traditional basins that release water at a constant rate, these systems can adjust how much water they hold or release based on actual conditions. That flexibility makes a big difference during heavy storms because the basin can hold back water at the moments when downstream areas are already stressed. This helps lower flood peaks, protect neighborhoods and roads, and make better use of the storage we already have. For our project, we built a demo-scale version of an actively controlled basin to show these benefits in a clear and hands-on way. Even at a smaller size, it highlights how real-time adjustment can smooth out storm impacts and make communities more resilient. Our goal is to help engineers and students see how this kind of adaptive approach can improve stormwater management as flooding continues to become more common.
The main constraints for the demonstration system are the size, ease of transportation, and the water control. Since it's a demonstration system made to educate city planners and educators, it will be moved frequently. It must fit on a standard 2-foot by 4-foot table and be able to be taken apart for transportation. The dam around the catchment area must be at least 1.5 inches above the maximum water height to control the flooding, and all electronics must be housed in a separate, protected enclosure. Most importantly, the system has to have two actively controlled basins with measurable outflow so we can model multiple scenarios. To keep this project reasonable to be replicated by others, we plan to keep the material cost to under $500. If the active control mechanisms were used in a real detention basin system, the assembly would need to be able to withstand long-term exposure to the elements, and the mechanical components have to be fabricated from corrosion-resistant materials. The design would need to prioritize accessibility for maintenance and repairs, and security concerns would need to be taken into account since the system would be at risk to tampering and vandalism. The system would also need to not introduce pollutants into waterways or become compromised or blocked by debris. The solution we have created is a scale model demonstration system with two actively controlled detention basins that can react to stormwater flow in real time. The basins will have motorized gates that will respond to measurements from an ultrasonic depth sensor positioned above a weir in the downstream catchment area. Closing the headwall during large storm events will allow us to control the pipe discharge and prevent flooding. We plan to use a pipe connecting the drainage bucket to this dispersion system so all water used can be recirculated. As you can see in Figure 2, the basins will be made of clear acrylic, and the side of the upstream area will have a clear window so all of the scenarios can be seen.
As shown in Figure 3, the physical active control mechanism consists of three primary components: the headwall, the drive gear, and the movable gate. The system is actively controlled by a stepper motor connected to a microcontroller. The control algorithm controls the gate position by rotating clockwise to retract the gate and increase discharge, and counterclockwise to advance the gate and restrict or fully close the outlet. This control allows the outlet structure to dynamically adjust to variable hydraulic conditions downstream.
The active detention system will model 5 different scenarios to show how active control can be used to improve various types of detention systems for a variety of storm events. These demonstrations will help educators and city planners understand how actively controlled basins can reduce flood risk and improve nutrient management in a wide range of real-world applications. The first scenario involves no active control. Both basin gates remain fully open, allowing unrestricted flow into the catchment area. The second scenario involves flow through only the traditional basin, which is actively controlled based on the flow reading by the weir in the catchment. The third scenario involves flow only through the bioretention basin, which is actively controlled based on the flow reading in the by the weir in the catchment. The fourth scenario involves sequential basin operation, where the basins are actively controlled one at a time to simulate a response similar to the first flush. The first flush is the initial runoff flow after a dry period that contains the highest concentration of pollutants. Water will flow through the bioretention first to filter nutrients. In the final scenario, both basins are actively controlled. The flow chart shows how water moves through the system. Water enters the model by flowing into each detention basin. If the active control mechanism for each basin is closed, water is held in the basin. If the active control mechanism is open, water then flows through the outlet structure and into the tributary. Next, water flows into the rectangular weir, where height is measured using an ultrasonic depth sensor. From this measurement, flow rate is calculated and sent to the active control mechanism. If the flow rate is too high for downstream conditions and it is not supposed to flood, the active control mechanism closes, lowering the flow rate to prevent flooding. If the flow rate is not too high, the active control mechanism remains open and the flow rate stays the same. After the scenario is modeled, the dam is removed, allowing water to flow into the drainage bucket and pipe. Finally, the water is pumped back to the beginning of the system, where it enters the detention basins depending on which scenario is being modeled.
Moving forward with our project for next semester, we have a few things to address. First off, we will need to finalize the weir's position within the catchment area. Doing this will require testing at different positions. Next, we will need to confirm how the upturned elbow will be integrated into the bioretention basin. This will also require testing for how high the position of the elbow could be due to head within the basin. Lastly, all the design components will need to be constructed with portability as a priority, since the system will be moved to different areas for education.